Hello and greetings from State College. I'm very happy to be asked to take part in this special session in honor of my friend Paul Baum. And even though I can't be physically present, I am glad that technology allows me to be with you virtually. So without further ado, let's move on and do some mathematics. One of the things I learned from Paul and also actually from Dan Quillen is that you can never spend too much time thinking about the mysteries of the Bott periodicity theorem. For us, Bott periodicity is a theorem about C-star algebras, and we formulated in this way that the K-theory, K0 or K1, of a C-star algebra A is naturally isomorphic to the K-theory complex C-star algebra, I should say, of the second suspension of A, where the suspension functor sigma of A is just defined as A tensor C0 of the real line. Of course, there are many ways to prove Bott periodicity, but the way I want to talk about today is, first of all, it's a way that doesn't work, but it's something that is closely related to coarse geometry, large-scale geometry, which, of course, is close to my heart. There's a fundamental construction which links coarse geometry with the theory of C-star algebras, which is this, that from a metric space X, you can build an algebra, we call it C-star of X, the algebra of finite propagation, locally compact operators on a Hilbert space over X, like the natural example is in fact L2 of X, where X has some measure. We can, even if we want, add a coefficient C-star algebra and form C-star of X with coefficients in an auxiliary algebra A. Now, if G is a group, we might think of a discrete group or even a Lie group with translation invariant metric, appropriate kind of translations, left or right, then there's a inclusion between two algebras we can form from the group. We can form the ordinary reduced group C-star algebra, C-star of G, here it is on the left, and we can also form the coarse algebra of G considered as a metric space there on the right, and there's a natural inclusion from one to the other. In fact, the existence of this natural inclusion is part of the reason for constructing the coarse algebra. It's supposed to be a substitute for the group algebra in the case where there is no group action. And yes, this works with coefficients as well. This inclusion becomes an inclusion from C-star of G tensor, the auxiliary algebra A, to this C-star of the metric space G with coefficients in A that I mentioned before. Now, I only want to consider absolutely the simplest possible case of this construction, where we take G to be the Lie group R of real numbers. Fourier analysis tells us that the C-star algebra of this group is just C0, the continuous functions vanishing at infinity, on another copy of R, the dual group. And so the inclusion that I mentioned before, and we'll put the coefficients in, becomes an inclusion from C0 of R hat tensored with A, which of course is nothing other than the suspension of A that we mentioned before, into the C-star algebra of the metric space R with coefficients in A. Now you can do some calculation using standard techniques of K-theory, and what you'll find is that this inclusion map induces an isomorphism on K-theory. It's not a very hard calculation. I encourage you to carry it out. But what's really interesting is that if we just knew the basic properties of K-theory, the 5.5 term exact sequence and homotopy invariance and so on as it's called, but not Bott periodicity, and if we also knew for some independent reason this fact indicated in red, then we would obtain a proof of the Bott periodicity theorem, quite different from most of the existing proofs. Let me explain why that is. So the first step in many proofs of Bott periodicity is to take a look at this short exact sequence where we have here on the left the suspension of A, here on the right A itself, and in between what's sometimes called the cone on A, that is C0 of a half open interval 0, 1 tensored with A. And this algebra, the cone on A, is what's called a contractible C-star algebra. Contractible, that is, the identity map on it is homotopic to the zero map. That means that all its K-theory is 0, and that gives us an isomorphism from K1 of A to K0 of the suspension of A. So if we could only find an isomorphism the other way from K0 of A to K1 of the suspension of A, then putting those two isomorphisms together would give us a proof of Bott periodicity. So it's natural to try and apply the very same idea and to wish for a short exact sequence with A on the left and the suspension of A on the right, and something which I've marked with a query here in the middle, which should also be contractible. Actually, having A on the left is not such a smart idea. A might be unital, and then it couldn't be an ideal in anything in an interesting way. But we could replace A by A tensor the compacts and still ask for the same thing. And now this is something that we really could go looking for. And indeed, this exact sequence is the basis of the proof of Bott periodicity given by Joachim Kunz, where the query algebra there is closely related to the Toeplitz algebra. But I'm going to go a slightly different direction, and what I'm going to show you is that we can find an exact sequence of this kind if we allow ourselves to replace sigma of A, the suspension of A, by the C-star algebra, C-star of the metric space R, with coefficients in A. And that means that we could prove Bott periodicity if only we knew, as I said at the beginning, that the suspension of A and C-star of R with coefficients in A have the same K-theory. So in the world of coarse geometry, if we have a metric space X and then a subspace Y in X, that corresponds to an ideal, let's call it IY or something like that, sitting inside the C-star algebra C-star of X. Basically, this is the ideal generated by operators which are supported near Y, and the ideal IY in terms of K-theory is equivalent to the C-star algebra of Y itself, considered as a metric space in its own right. We're going to apply this idea to two situations. First of all, the situation of a single point, the origin, sitting inside R+, and secondly, to the situation of R-, the negative real axis, sitting inside the whole of R. And let's see how that works out. So throughout this discussion, I'm going to be drawing diagrams of coarse C-star algebras, and I want you to assume all the time that we are taking coefficients in the C-star algebra and in the auxiliary C-star algebra A. I'm not going to keep writing that to avoid taking up too much space. So first, let's think about what happens when we have the origin sitting inside R plus. The exact sequence looks like this: 0, and then the ideal associated to a point or to any compact subset is actually always the C-star algebra of compact operators. So here we have the compacts, or for this one time I'll write the coefficients compacts tensor A. That's an ideal. It sits inside C-star of R plus with coefficients in A as assumed. And then there's a quotient algebra. I'll just call that Q. And then 0. Now let's think instead about R minus sitting inside R. And now our exact sequence looks like this: 0, C-star of R minus, or really the ideal associated to R minus, but as I said, that's equivalent in K theory to C-star of R minus, then C-star of R, and then another quotient, Q prime, and then 0. But if you think about it for a moment, Q and Q prime are actually the same thing. Taking operators on R plus and modding out by those which are supported near the origin is exactly the same as taking operators on R and modding out by those which are supported on R minus. And I only need to tell you one more thing and then we're done. And the one more thing is that C-star algebra of a half line, so that would include in this picture both C-star of R plus and C-star of R minus. C-star algebra of a half line is contractible by an argument which involves an Eilenberg-Swindle argument, which Nigel Higson first showed me. So if you take all of that together, you see we've got a short exact sequence, 0, the compact tensor A, then a contractible thing, and then there's Q. And this other short exact sequence shows us that this Q is equivalent in K theory to C-star of R with coefficients in A. So putting it all together, we have exactly what we want: an exact sequence which has A on one side, C-star of R with coefficients A on the other side. If we only knew that C-star R with coefficients A was equivalent to the suspension of A, we would have proved the Bott periodicity theorem. It's a tantalizing situation because C-star of R, the group algebra here, sits inside C-star of metric space R, the coarse C-star algebra, metric space algebra, in a very canonical way. It sits inside it as the subalgebra of translation invariant operators. And it's tempting to believe that there is some process which involves taking a generic element of C-star of metric R and averaging it out some way, maybe over Follner sets, to make it translation invariant, and thereby to prove that this inclusion is an isomorphism to give an inverse to the map that it induces on K theory. But I've never been able to think of one. So I leave that as a little mystery, and maybe as a tribute to Paul, because one of the things that Paul really taught me was to be happy in the face of the mysteries of mathematics. And I am just glad that his happiness and joy in mathematics is being celebrated at this event.